Hello everyone, my name is Atanas Kiryakov and I want to welcome you all to our latest Ontotext webinar. This one is actually the second for January, but it is the first one for the year with speaker our CEO Atanas Kiryakov. So it should be very interesting to watch. Before we start, I would quickly introduce him and go over a few housekeeping details. So the topic that he's going to discuss today is how RDF levels the advantages of labeled property graph, how it keeps the three key benefits, which are standards, semantics, and interoperability. So Atanas Kiryakov, he is the founder and CEO of Ontotext. He has a master's degree in AI from the Sofia University, and he is a board. He is a member of the board of the Linked Data Benchmarking Council. He's also a partner and part of the board of directors in Sirma Holding Group, which is one of the biggest IT companies in Bulgaria. Today, he is also a top expert in graph databases, knowledge graphs, and many of the surrounding technologies. So housekeeping details. As always, this webinar is live and recording to it will be distributed to all of you most probably tomorrow. Currently, you are all muted, but this is to reduce background noises and to enable Nasu to present without any interruptions. This doesn't mean that you cannot communicate with us, no. You can by using the question box in your GoToWebinar panel. We actually strongly encourage you to do that because at the end of this webinar, we have planned a 10 to 15 minutes Q&A session in which Atanas will try to address all of your questions. With that, I would now like to give the stage to Atanas. So Nasu, the floor is yours.
Thank you. Do you see my screen now? Do you see the presentation?
Yeah. Yes.
Okay, wonderful. So thank you for joining us today. Let's start with a quick introduction. I founded Ontotext back in year 2000, and it was the pioneer years of the semantic web and later on the semantic technology. And we've been part of this community that went through the transformations of aiming at dealing with content, with semantics, with data in a much better way, in a much more connected way, a distributed way, and being able to reason about the data and automate more tasks. So implementing this big vision took quite a lot of different transformations and some failures and then new names and things. And we've been part of this process for the last 22 years. Now we are mostly known as the developer of GraphDB, the database engine, and we are also totally leading one of the applications of this technology, that is knowledge graphs. We are also very, very proud and very, very happy to be a center of an ecosystem of more than 20 partners. I'll talk about this later on. On the bigger picture, yeah, we are profitable, growing, self-sufficient. Most of our clients are multinational companies, although yeah, most often the deals go through US, which is normal. That's the biggest market of this technology also, and we have a long list of very, very wonderful clients and interesting implementations across different sectors, from banking to finance to healthcare, national security and whatnot. On the bigger picture, we've been always part of the community who develops these trends and the standardization and what's coming down the road. That's why we are part of W3C, where all these RDF and the related query languages and all sorts of standardization of this tech takes place. as well as several other associations and organizations that are relevant to this sector. I made a sort of graph trying to explain what we do and why and how. So let's give it a try. So on the very big picture, we are connecting the dots of your enterprise knowledge, or somebody's enterprise knowledge, and it's an exercise of combining and let's call it smartening up the proprietary information that each and every enterprise has in wide diversity. So it is a big challenge to put it together and to do the integration, but it's not all of it. There is much more to be done in terms of making it useful. Part of our special sauce is that we've been always using deep domain knowledge, as exhaustive as possible, volumes of domain knowledge that provide background and can allow for the smartening up of proprietary information by putting it in context, but linking all sorts of relevant concepts in the way in which a human expert in the field has this domain knowledge, which helps him or her do something useful with your proprietary information. That's our vision, that we should do as much as possible of this when we're smartening up and helping computers do clever things with your proprietary information. So we use deep domain knowledge to enrich and to provide context for better interpretation of proprietary information. Technically, it's about doing knowledge graphs. That's the way we do it, and the technology stack that we use to do it. And these knowledge graphs, at the end of the day, enable unified views and analytics across diverse data. To put them together, there is a lot of work to be done in normalization and linking and reconciliation of data across different sources. Essentially, it's not just us. Everyone who is in this business of trying to put this data together in a meaningful way, one way or another, is trying to automate it by means of text analytics and data analytics. Again, what we do in a different way, in a special way, is that again we've been all the time trying to use deep domain knowledge and really big volumes of background knowledge to also make this linking and reconciliation better. By to give you an example, if you work with geonames, which is quite an exhaustive source of geographic knowledge, this can often help you reconcile locations of clients coming across to different databases in an enterprise, where you have a couple of strings denoting some addresses, and putting them together without an external source of geographic knowledge can be very hard. So to finish the deep domain knowledge story, it helps in several different ways in connecting the dots of your enterprise knowledge and getting more value out of it. For a moment, going back to the technology, our GraphDB is the engine that we've been developing through the years as a database engine and also search engine for knowledge graphs. And the big missing thing is why we do all this and why I've been telling you this story. What's the value in it? Well, at the end of the day, it's about getting better results and fuller results in less time. And that's everything that this complexity is about. That's everything that GraphDB is designed for, is to basically give you much better experience in discovering things and getting complete answers to sometimes quite complex questions. To do this, well, there is a lot of technology ground to be covered to enable this conceptual picture. And for knowledge graph management platform, there are a lot of capabilities to be covered in terms of building these knowledge graphs, and then how you store and index them and how you query them, and all sorts of capabilities needed on the operations side, of all the way from access control to availability and stuff like that. Or what are the interfaces and the APIs and the languages and the buses that other applications use in order to consume these data and to access these knowledge graphs. And then at the end on the right, you can see also, well, this is the consuming the knowledge graph and taking the value out of it. So it's all about having better ways to explore information or to do analytics in a way people weren't able to do this before. So that's quite a busy map. And indeed, there are that many things that you would expect. And if you get an RFI for a linked data platform, knowledge graph platform, or something like that, you see questions about all these different capabilities quite likely. So we made conscious decision that we will do our best to provide very solid offerings for some of these capabilities. That's what you see in orange. If you want, a lot of this is around database engine and storage and indexing, how availability and operations and all sorts of access things. But we have also covered quite a lot in terms of analytics and search and visualization. Still, we said no, there are areas where we don't want to go ourselves. That's areas in which we will partner with the best providers of such technology on the market, be it taxonomy editors or ontology management tools, data catalogs, or even chatbots. That's our way of thinking. As a leader in this RDF space, we want to have an ecosystem of partners around us, and that's the ecosystem in the RDF part of the stack. And there is a whole bunch of other players which are in the labeled property graphs space. So the essence of this, the main story in this webinar is essentially how RDF managed to address all the advantages that labeled property graphs had historically, which the only tangible ones would typically be, well, in Thinkerpop, in labeled property graphs, you can attach properties to the edges of the graph, and you can't do this in RDF, which is pity, because sometimes you need it. And then the second criticism was, in Gremlin you can traverse a graph in a very efficient manner, and triple stores are not good at this. And this was true up until a few years ago, but there are a couple of things that changed this story. RDF-star is one of them, which is a very powerful mechanism to attach metadata to edges in the graph. And now also all the major triple store vendors, RDF engines, provide extensions of SPARQL that cover very well multi-hop relationship discovery in graphs and searching paths and stuff like that. So to the rest of this presentation, the two big topics would be RDF-star and what it is and how it works and how the different implementations across the vendors work. Then the second big topic would be a similar overview with respect to graph traversal and how it is implemented in RDF-star and how it compares to some of the LPG engines. And even how, if you're in the RDF stack, you can take benefit of what's natural there. For instance, using semantics to do reasoning, and how this can help quick graph traversal. At the end of the presentation, I'll share our views on what is the real added value and what is the gist of the knowledge graphs, and yeah, how RDF serves them very, very well. So let's get it started. In RDF, everything is triples. We all know this. And one of them will be Abraham Lincoln, President of the United States. Obviously, you can provide labels, but that's still the reality. If you look at Wikidata, what is the actual information about this relationship that you want to have somehow modeled and represented? It is much richer set of features. This relationship between Abraham Lincoln and the presidency of the United States, and it's more information like contextual information, temporal and whatnot about the relationship itself, as well as provenance information like who, when added this piece of information. So the big question is how we represent this metadata in RDF, and we have the answer now. RDF-star allows you to do so. So you can make statements about statements. So if you have the core statement being Abraham Lincoln held the position of President of the United States, you can make statements about this one and say, well, this whole thing, the start date for this relationship was 1861, and you have syntax that allows you to do this in all sorts of RDF serializations as well as in SPARQL. That's the essence of the RDF-star, the essence of the RDF-star recommendation that is part of the WTC standardization process. And that's much more powerful than what you can do with property graphs, because here you can make all sorts of RDF descriptions about a single edge. So you can attach really expressive metadata, not just key value pairs, the way it works in property graphs. This was possible in RDF also before RDF-star. So you can see different ways of, there was always reification in RDF from day one. And then you can also represent this with any relationships and singleton properties and singleton name graphs and stuff like this. Most of these were very unhandy, and they were making it even more complex to model this metadata this way, and after that to consume it. So the biggest thing about RDF-star is that it removes all sorts of modeling complications and just allows you to do what you want to do. It's make statements about edges, express more information about edges in the graph. If you want to see this visually, you can think of it like a statement that starts from the middle of an edge and then has again a predicate and an object. We made some experiments on how these different ways to express metadata differ. So we took a fragment of Wikidata in RDF, and then we compared the volume of this fragment. If you use standard reification, it is close to 400 million statements, and it would take close to an hour to load this data in GraphDB, and it would take whatever impact on whatever footprint in terms of storage. Then if you do this, it's slightly better, but marginally better if you do this with any relationships. And then there is further improvement if you do it with named graphs, but RDF-star, particularly in the way in which we properly implemented it in GraphDB, makes the number of statements that you need to express the same metadata, as well as the time to load it, almost half the one of the RDF verification. So there are measurable gains in terms of just using this mechanism of what it takes in terms of space and time to represent metadata in a source like Wikidata. That's something that we all see in many other contexts. We also have another use case. One of our partners, Synaptica, they have a taxonomy management system called Graphite, and that's one of the leading vocabulary management tools. Graphite uses GraphDB to basically manage all sorts of taxonomies and vocabulary management, controlled vocabularies that you can deal with there, and it's essentially SCOS representation of some knowledge and conceptual structures. So for quite a while, Synaptica had hard time to manage the access control information, like for a specific for specific property, for instance, which users would have to access it, given what project it is part of and what scheme it is part of, and stuff like this. So before, with the vanilla RDF, they managed to represent this access control information using essentially any relationships, and it took like 5 statements to get this right and to establish these relationships between users and projects and property and scheme. And with RDF-star, they've been able to do this in just 3 statements. So it made it simpler and lighter weight for them to manage this access control information in Graphite. Now, when you go to represent to implement RDF-star, there are a number of corner cases to take care of. So, for instance, it's nice that you can make statements about statements, but then can you do statements about statements about statements? So, how many levels of nesting you can do there? And if you go to GraphDB and to place graph, you can do as many as you want. That's not the case with Stardock and Anzo. There are also corner cases like think of that. Imagine the case you're using RDF-star to track changes in a graph. So you want to keep information of who and when added a specific edge in the graph, and who and when deleted it. So for when it's about who and when added a statement, that's still there, it's simple. But think of the situation of provenance information and tracking, keeping history of who and when deleted something. So this requires the capability of being able to hold metadata for non-existent statement, for a statement that was already deleted. You can do this in GraphDB. You can't do this with most of the other engines, and so on and so forth. There are quite a number of these corner cases, and we took care to address all of them one by one. So with this, I'm done with the RDF-star part of this presentation. So now let's dive into graph traversal. For everyone in computer science, we know from some of the first years in the university that finding a path in a graph is computationally a very heavy problem. Doesn't matter whether you do it depth first search strategy or breadth first search, and this task can have a number of varieties. It could be just checking whether 2 nodes are connected, or it gets more complex when you're not just checking whether there is a connection, but trying to find the shortest one. And it's even more expensive if you try to find all possible paths and stuff like that. So that's known to be challenge on the one hand. And on the other hand, there are quite a number of real-world use cases in which you need it. The most obvious one being finding a path from point A to point B in a map, in a navigation scenario. But you have the same in supply chain analysis, so in recommendations or social network analysis, finding friends of friends and stuff like that. So there is countless number of use cases in which you need to be able to do this. So this was sort of possible with SPARQL before that. In SPARQL, there is something called property paths, which allows you to say, well, I'm trying to discover a relationship between node A and node B, and that's the pattern of relation of path between them, where you can put some restrictions on I want to see edge with this label first, and then a number of edges with that label, and so on and so forth, like in regular expressions. So it's actually quite powerful. What property graphs doesn't do is that they tell you which are all pairs of statements between such property paths can be found, but they don't tell you the paths. So they tell you, I found one, or I found 330 such pairs, or 330 different paths, but in the SPARQL 1.1, there is no way in which you can get these paths back. So it's a bit like the engine is telling you, I know the path, but I'm not going to tell you what this path is. This is workaroundable in SPARQL, but yeah, the queries become really ugly, and also usually very slow, because you're putting an extra challenge to the query optimizer. So to address this, essentially an extension of SPARQL 1.1 was needed to get there, and we have our own extension, which is SPARQL compliant with SPARQL specification, because it uses the very standard syntax with specific predicates, like if you use this path search, that's essentially telling to the engine that now we are about to specify a path between two that we want to search for, and then you say, well, I want to find all paths, and then you can say you can provide the source node if you want to have it bound, or it could be also a free variable. You can tell the destination node if you know it, or you can leave it unbound so that you can find all possible destination nodes. So you can specify this problem for instance, if you want to limit the complexity and limit and say, well, I don't care about paths that are longer than 3 hops in the graph, and then you can say max path length 3, and quite a number of other things. And of course, you can provide a pattern saying, actually, I'm only searching for relationships which are on each of these steps. You have two more granular relationship. One relationship between in the graph that says that somebody knows somebody, and that's usually in this representation, a relationship between accounts in a social network, and then get the person associated with this account. So that's the pattern, and that's the normal complexities when you have to deal with real data. We have also a way of course, of specifying shortest path, and all sorts of variations, like saying, well, if you say bidirectional true as a parameter, it says well, I don't care about the fact that this graph is a direct graph. So I'm happy to find relationships. That doesn't matter in which way they go. To find the multi-hop relationship doesn't matter how the directions of the specific edges are set. And that's yeah, just the way in which such things should be implemented, and what should be possible to make this really well-defined functionality. We wrote our homework to find and to analyze how other engines implement the same functionality, because most of our competitors does have some sort of support for searching paths in a graph. And then in some cases, yes, for some of the engines, this was implemented by altering the SPARQL syntax, which is, from our point of view, a very inappropriate thing to do, because you essentially forking a SPARQL parser, and it becomes really to govern these queries and to do all sorts of to implement all sorts of discipline. If you do this, then some of the engines can be asked to do this kind of, to return only distinct paths, so you don't have to in the application to sift through multiple rows which actually give you one and the same path. And then some engines support wildcards through undetermined predicates of the relationships in the path. Some don't. So yeah, again, it took us a bit longer than others to implement it, but we want to make sure that we check all the boxes. And then beyond just checking the boxes, we took care to benchmark it. We are part of the Linked Data Benchmarking Council, which is like the TPC for graph databases. That's a non-profit organization, non-profit organization of all the major vendors, Ontotext and Neo4j, and CWI in Amsterdam, and Sparsity and some others, UPM. We've been the founders of LDBC almost 10 years ago. And now we also have Amazon and Oracle and TigerGraph, and as pretty much really everyone in this community being there. And in Linked Data Benchmarking Council, we develop benchmarks, of course, as well as the same body is used for standardization of some of the new graph query languages like GQL. But back to the benchmarks. So one of the benchmarks is the social network benchmark, which was initially developed by Neo4j, although they never benchmarked themselves and published results on it, but that's life. And it's probably the most comprehensive benchmark. So in the graph databases and the graph analytics world. There are several, actually multiple people who defend their PhDs just on the data generator for SNB, to make sure that it doesn't matter how much you scale with, it will be a good graph. You have the right representations of the data and patterns, so that it is close enough to the real world, but there are no easy ways of cheating it and essentially reverse engineering the patterns of the of the data generated to improve performance in a way in which it's not going to work in the real world. So it's very comprehensive benchmark in terms of how data is generated and how what the connectivity patterns and the distributions are. So that's roughly what it looks like. Okay, a snippet of data from the social network benchmark. So as you see, it's about people who know other people, and then there are also relationship information about in which the location of the people and relationship to a given city or employers in terms of companies, so where people studied and so on and so forth. So it's not too complex, but it's not trivial either. And still, when you do have different sets of queries for the same data set. Some of them are interactive queries, some of them are more analytics oriented, for really not for database engine, more for offline analytics platforms. So we've been focusing on the SNB social network benchmark interactive query set, and there you have queries like given a specific person, tell me all the people that are connected to it via up to 3 steps of nose relationship, or find the shortest path between two persons, and so on and so forth. So so we decided to use this benchmark to see, apart from checking all the boxes of all the special cases, whether the path extension that we implemented, graph path search extension that we implemented for the engine, does perform well, and whether we can really address the claim of the white man can't jump and RDF engines can't efficiently traverse graphs. We are in the process of scaling up the experiment, so we started really low to see how it works, and now we are benchmarking the levels of scale factor 30 and scale factor 100. The later being scale factor 30 is a graph with 1.5 billion triples, and scale factor 100 is 5 billion triples. So it's quite sizable graph and a good problem to have. One thing that we want to do is to implement this without using too much memory. So without counting that you can put 5 billion edges in the memory. So we are trying to strike a balance in which you can do this type of tasks even for very large graphs without special hardware and really expensive machines. And we also want to benchmark ourselves against some LPG engines for which we've been able to run the test. And I gotta say that when compared to some of the popular ones, we are getting quite good results. There are queries in which they do better, but overall we're getting very good average score, and we keep improving it. So we've been working for this for like half a year now. There is also one thing to mention, is that their queries were initially they've been quite tedious to deal with, because just the cardinality of the data, how quickly the breadth-first search spans, if you want, because of the degree of connectivity in the graph, and the size of data was such that query like Q11, it was taking like 25 seconds to deal with. If we don't do something special, we had hard time to figure out what is the best way to deal with it. What we found was that okay, we can probably use inference and essentially do shortcuts in the graph of saying, well, if you all the time have to search for patterns of a person that knows someone that has a person and so on, we can use very simple reasoning to infer this direct nose relationship in the graph, and then to make a simpler version of this query. And then out of a sudden it became like 30 times faster. So it was already a quite normal sub-second query response when we use reasoning to shorten the paths in the graph by introducing these shortcuts. And that's something that GraphDB does in a very efficient manner. It's really worth the cost of reasoning for which is very minor overhead to have such a big gain in query time. So that's how reasoning helps graph path traversal by shortening the paths. Okay, so to this end, I covered all the more technical things of the direct shootout of how the RDF stack and GraphDB addressed the historical advantages of the labeled property graph stack. And now I want to entertain you with slightly less technical things and a higher level of like our value, our thinking and our understanding of the added value of knowledge graphs and how RDF fits there. So think of different problems like monitoring IT systems in a very big retail bank, or putting up a platform for oil and gas market intelligence, trying to source signals across different databases and news and stock messages and stuff like that. Or the problem of being an M&A investment banker who is trying to have a full view on all the M&A transactions on Earth, with geographies, industry sectors, who bought whom, what the subsidiary relationships are, what indirect control chains are all there, and stuff like that. That's really serious graph and use case. Or the problem of a building management system that essentially that's at the heart of the operations of a big skyscraper. So that's a system that holds the information about the elevators, about the lighting, about integrates information about across the different systems and elevators, lighting, ventilation, security access, and quite a few other things. So there are literally thousands of devices of different types with different software uploaded to them, with different connectivities and dependence and positioning within the building. That's a complex graph, and that's a complex information to deal with. And still, in our experience, that's simpler than handling an inquiry from FDA about side effects of drugs. And then if you are a pharma company, you gotta make a very thorough search in all the clinical trials that you have. And these are 100 page long PDFs, and searching there is really tough. So what all these problems have in common is that you can solve them very well with knowledge graphs, and the best way to deal with this is that in all these projects, usually one of the mainstream players have failed to get this right, or to get the client calling us. We've been able to provide a successful solution and in reasonable time and budget to these problems using the knowledge graph paradigm. So what's in common, like the underlying complexity, is that you have to provide a unified view across diverse databases without centralized context. Quite often there is also unstructured content involved, and again, very often you gotta combine your proprietary information with external data, with some global knowledge that is really necessary to nail the problems down and to get to the right set of information. So knowledge graphs really shine when you have a problem that requires comprehensive domain knowledge. So think of domains where you have to deal with hundreds of thousands of concepts. So an enterprise taxonomy of a few hundred or few thousands of terms is just not going to make it in biology or in investment banking, because to get it right, you got to deal with millions of concepts in the life sciences, or millions of companies, or really big volumes of technical knowledge and stuff like this. The other thing that can make a task a different type of complexity that may bring knowledge graphs as a very viable solution is when you have highly interconnected reference data, like if you can consider a database of all companies on Earth that you can buy from one of the vendors. It is an example of highly interconnected reference data, because you have all sorts of very diverse relationships between these different nodes, between these different companies and the people and the locations and stuff like this. And then there are also domains in which you to get it right, to be able to address the questions and to serve the information needs, one should pay very good attention to the semantics of the relationship, like in the life sciences. Just finding a path in UniProt is rarely somebody cares about this. So it's always about the 10 different ways in which a specific relation could be expressed in direct or indirect manner. And an engine that can deal with this really makes a lot of difference and makes it easier to deal with such domains. So from a more business point of view, the competitive insights always come from better intelligence. And this requires deeper understanding of a domain and being able to deal with really diverse signals from different sources and from diverse data sets. And to do this in an instantaneous manner, so rather than doing it all overnight, is just not useful. So you need a tool, a platform, an approach that allows you to continuously unify data and update data with instantaneous updates. So that's what we know how knowledge graph can serve well. And we have seen a really wide variety of applications across content management and knowledge management. Data management, of course, is probably the main land for something that is data management technology. We nowadays see a bigger number of a growing interest in knowledge graph in like manufacturing and aerospace and infrastructure management and energy, where people need to deal with very complex technical knowledge and to maintain infrastructure with a lot of connectivity. So deal with complex supply chain, supply chains. So these are all sorts of applications in which comprehensive domain knowledge really matters and can make difference in how good you perform in each of these applications that you see as terminal nodes here. Well, the added value is essentially what makes knowledge graphs good for all these different applications. They can serve as hubs for data content and the metadata that also all sorts of flavors of metadata that you can associate with them. So what makes real difference is to have no metadata in terms of key value pairs that nobody knows how to implement, but rather to have a structured metadata, semantic metadata, where it is very easy to interpret the meaning of the different pieces of information attached to your data and to your content. So the way in which the magic works is that well, linking data and essentially having a platform that that has a graph underneath and interconnecting things, and having this in the core of the representation gives you the benefit of a network effect, that when you have two connected entities, like in a dictionary or encyclopedia, they can easily describe one another, like in Wikipedia, and essentially a network of concepts allows much more interesting ways to interpret these contexts as compared to just a table or a list. And then if you have a connected body of entities in the range of hundreds of thousands of entities, that's actually what we call an expert. That's the PhD level of that you get, and that's the purpose of many university courses, to essentially make sure that you know the 100,000 connections concepts that matter in this domain, and what the connections between those are. Then being able to what's very important in knowledge graph story is to attach semantic metadata and to overlay semantics on top of this data to make sure that there will be no ambiguities and there will be no misinterpretation, which is very easy when you get information that is stored in a database for one purpose, and then you get it out of there and make very often there is a lot of information that is lost on the way of what price meant in this specific database, with or without VAT, and very simple things like this, but you have a lot of them. And if you have semantic alignment between the schemata of the different sources, when you integrate data from a specific source, when you take care to have formally described the semantics of different pieces of information, this allows for unambiguous interpretations. In most of the other cases, you're essentially, it's very easy to misinterpret data. So if you have all this set up with the semantic data model that gives a clear interpretation of the data, and if you have a stable reference data, or at least well-managed reference data with good data identifiers, that's essentially the recipe for easy updates, and also the recipe for making this body of data easy to reuse across different applications. And that's the magic of knowledge graphs. Now, how is RDF making it? What makes RDF good fit for this? Well, it's the explicit semantics. So with RDFS and OW and SPARQL, you have different ways to express semantics at the schema level, so that the computers and different systems and applications that can use it can understand the meaning easily and automatically. And then it also helps for good data quality, because semantic schema, particularly in the case with RDF shapes, allows for data validation. That's the key to good data quality. Interoperability due to all sorts of protocols for federation and remote access that you don't have with the LPG world. Native web syntax with global identifiers, and On top of these, there are already thousands of data sets that are readily available for reuse, like the GeoNames that I mentioned, or Wikidata, or another source. And finally, you have all these well covered by standards, all the way from query languages to data representation to syntaxes, serialization, syntax, and stuff like this, schema queries. That's not the case elsewhere. That's all these things which are the benefits of RDF for serving well RPG are essentially what LPG lacks. There is no more explicit semantics. There is no interoperability because you have nothing to help you perform a federation between two property graph engines. And yeah, standardization efforts are only starting. So having said this, I want to comment briefly on a few use cases. That's actually from a report from Georgia and Diotis and GigaOM Graph Database Market and Graph Databases Market and Technical Analysis. So quite likely, if you are a data scientist working on a very concrete analytics problem, and you just want to fetch some data from somewhere and do your analytics. The simplicity and the wide all sorts of tooling that you can find with property graphs are likely to make you to attract you. So I should admit property graphs would have some advantage in this case, although you can do the same with RDF. But if you are an architect who is designing an enterprise data management system, content management system, well, the presence of schema language in property graphs, you don't have schema language. So it's essentially for enterprise data management. This is a disqualification criteria. You not being able to express to have a contract on the schema of your data, doesn't matter how much you want to enforce it and how flexible it is essentially a showstopper. And then all the capabilities that you have with RDF for expressing diverse metadata and properly modeling them is badly needed in content management systems, and again, you don't have it. You have nothing to help you there with the property graphs. So across data management, data governance, and operations teams, all disciplines and standards that come with RDF are preferable. If you are building a single application that is going to work with a single database, well, you can do it in many ways, but it's likely that people would go again to label property graphs. So that's the quick comparison of George and Diotis on the subject. So with this, I'm closing this story that got a bit longer than expected. Well, RDF engines just check all the boxes and take care of everything that you care about if you want to use knowledge graphs in a proper meaningful way, not just to get an arbitrary network and call it a knowledge graph. The RDF is a simple but very powerful RDF model, and with RDF-star it's now also easy to attach metadata without complications. You have the standards and you have the semantics, the formal semantics, and everything that you need for enterprise data management. And recently you've been also in this space, we caught up with all the optimization specific taking care of graph traversal. Well, with LPG, well, there are still some cases in which that there are good reasons to choose it. One of them would be if you want to have very tailor-made, micromanaged procedural graph exploration, then Gremlin is your tool. And also, if you are in the business of running some very heavy analytics on a on an entire wardrobe with terabytes of data. Again, yeah, property graphs will serve you better. For everything else, yeah, RDF is the better choice. So thank you. Thank you for staying that long. And I'll be very happy to take questions. So yes, and did we got questions?
Thanks, Nas, for the presentation. Yeah, we have quite some questions. If you want to take a look at them, take a minute to. Probably we won't have time to answer every question, but every question that is asked, we will answer it tomorrow, and we will send it via email with the recording. So you will receive an answer to your question regardless or not, whether we cover it now while we are online or not, because we are ahead of time.
Really, that's a lot of questions. I'll start. Yeah, top down. No, just a second. I'm getting used to this tool. Can we receive a copy of the slides? Of course, yes. So I see Yasin already answered the non-technical ones, so I'll focus on the rest of them. What's the source of the current slides? Oh, that's me. That's our slides. And yeah, you get a copy of the deck. Yeah, okay. So Robert Alexander is asking about the bull's eye diagram in the beginning with the different database engines. That's from boutique research company called Boor Research. So I'm getting there. So that's this one, and you can see a reference there. So it's GraphDB, Graph Databases Market Update 2021 from Boor Research. Okay. So yeah, it's really a long list of questions. I'll leave the more technical ones for yeah, for later on. I see a question on the President of the United States diagram. Okay, that's going too technical. There was a question: is RDF-star supported, and how well in open source repositories such as Apache Jena? I do believe Jena does have support for RDF-star. RDF4J also has support for RDF-star. We are one of the contributors of RDF4J, and part of our effort to implement RDF-star properly was contributing all sorts of improvements to the parsers and other things that were necessary to RDF4J. So the only thing that you gain with GraphDB, the commercial version, is much more efficient querying and presentation, which you can get from the free version of GraphDB also without any limitations. But yeah, the basics are there with both Apache Jena and RDF4J. Okay. Regarding the benchmarking against LPG engines, GraphDB appears slower on load and updates. How much slower? That's questioned by Yuri Simone. Okay, we'll take care to send back some data to you. But it could be the difference between loading a very big data set for 1 hour instead of 20 minutes. So it is slower. But if we're speaking of billions of triples, an hour is not something that's really an issue usually. Okay. There is a question: how does GraphDB compares to OpenLink Virtuoso? Well, we basically pick to compare against our more visible commercial competitors and those that are more often we have to compete with and that are more often considered on the market. So Virtuoso is not in the top 5 list of these engines. And when speaking of RDF-star implementation and Neo4j, there is nothing to compare against, so it's just not in there. Speaking of how GraphPath extensions of SPARQL, again, that's irrelevant for Neo because Neo is not a SPARQL engine. They can do all these things in Cypher. It's only that Cypher is not a standard and SPARQL is. Okay, let's pick some other questions. Okay, and then you Simone has a qualifying questions like, okay, loading and updates are slower. Can we fix this in the future? Yes, that's what we're currently working on. It will probably never become exactly as fast as with some of the property graph engines, which in many cases, if you have a platform that is entirely oriented towards analytics and doesn't care about, for instance, all sorts of ACID requirements or interoperability requirements, and you don't have to deal with global identifiers and stuff like that, it will be probably a bit faster to load the data there. But it's not an order of magnitude difference. It's usually a much smaller difference. So going to the bottom, I see a question from Axel Delso. Is it possible to constrain a graph traversal in a specific graph name context in the workbench? Well, let me check this with the GraphDB team. Of course, you can essentially when you go there, if we go to the sample syntax of searching paths in SPARQL. So if you look at this example, you have this service path clause where you can provide the pattern that you're searching for. I do believe you can have a named graph inside this service statement, and then it will only traverse edges that are from this named graph. So yeah, this should be possible, but yeah, we'll double check it. So I believe with this we covered most of the questions. Thank you for all the 71 people that are standing longer than expected. We will provide also the answers and the recording later on, as always, including for those who registered but didn't manage to come. Yasin, do you have some closing words to the audience?
No, thanks, Naso. Thanks everyone for joining. It was a very interesting presentation. So see you on the next one.
Yeah,
Bye-bye.
thank you everyone. Bye-bye.